In this video, I will be going over a worked example of finding the volume of a washer, or finding a volume using the washer method. The washer method is basically just following the formula of to find the volume of this solid rotated around a certain axis, kind of like that. It would be equivalent to whatever terms we're going from. So for 0 to pi, it would be from the integral from pi to 0 of the function that is on top minus the function on the bottom relative to the axis of rotation. So here the axis of rotation is -1, which is going to be about here. And we have varying, we have two function segments. So at one point of this volume, the y equals sine x is on top, and then at another part of the function, the y equals sine 2x is at the top. So it's going to be actually two integrals from whatever these points are added. Basically, just the function of sine x squared times pi minus the function of sine of 2x squared times pi. That would be the setup if this was consistent, but it's not. First, we have to find, again, where these functions meet in the middle. To do that, I'm just going to simply set sine of x equal to sine of 2x. By using the arcsine function, I would just get x equals 2x, and then x equals 2, which would not make sense. All you have to do is subtract 1. 0 equals x, which doesn't make sense. Going back, if we divide by both sides, we're going to get 1 equals 2, which doesn't make sense. So what we have to do is something else. Sine of x minus sine of 2x equals 0. And then by using the arcsine function again, we get x minus 2x equals sine of 0, or arcsine of 0. And the arcsine of 0 is 0, so it's negative x equals 0, which gives us this solution, but we need to find this one. So we could estimate, or there could be another thing to do. You won't have to actually do this, more likely than not. But if it does have to happen, you could use your graphing calculator and just find the point where they equal each other, which would be at pi over 3. So pi over 3 is going to be the point where these two change, and that is where we're going to switch the integral from sine of 2x being on top to sine of x being on top. For the first leg of the function, sine of 2x is going to be on top, which means that the area function for this segment is going to be sine of 2x squared minus sine of x squared. This is what you'd think it would be if it was from rotating around y equals 0, but it's not. It's actually rotating around y equals -1, which means that if you use this normal thing, this normal function of the area squared minus area squared, then it actually would be wrong. This is an example of a problem that you have to use a difference. Like you have to have a difference between the function where the function is going around 0, and then the axis of rotation, because the axis of rotation isn't at 0, it's at -1. That's the word that I was looking for. So rewriting the actual correct integral, it would be 1 or -1 minus sine of 2x squared minus -1 minus sine of x squared dx. And then distributing, it'd be 1 plus sine squared 2x. No, it'd be 1 minus 2 sine x, 2 sine of 2x, plus sine squared 2x. And then for the second leg, it would just be 1 minus sine x plus sine squared x. And then double checking for sign errors, we're foiling it out. So -1 squared is 1, -1 times negative sine is sine of 2x, which means that -1 times minus sine of x is sine x, which means that this would be a plus. So because there's two negatives, I guess they cancel out. So that means that since this one is literally the same thing, except it's just sine of x instead of sine of 2x, follows the same rule. Organizing this so that it's a bit easier on the eye. Sine squared 2x minus sine squared x plus 2 sine of 2x plus 2 sine of x. Oh shoot, it's not. That's another sign error to look out for. Negative. So sine squared of 2x minus sine squared x plus 2 sine of 2x plus 1 minus 1 minus sine of x. You can't cancel these out. If you try to do that, then it doesn't make sense because there's different angles. Oh no, don't do that. So, going to the actual part of integrating, we can't integrate this sine squared 2x yet. We have to use identities to make it into something different. Recall that sine squared x is equal to 1 minus cosine 2x over 2. Yes, that's what it is. If it's wrong, then I'll find out soon enough. So rewriting with that in mind, it'd be 1 minus cosine of 2x over 2 plus 1 minus cosine of 4x over 2 plus 2 sine of 2x minus sine of x dx. So the reason why this one's a 4x is because this already had the angle of sine squared of 2x, which means that this applies again. It doubles down. If I am making errors, I'd love for people to correct me, as I have to be tested on this as well. So with this, we can just do straight integration. It'd be 1 over 2 minus cosine of 4x over 2. This isn't the final integral, I'm just rewriting again. Minus 1 over 2 plus cosine of 2x over 2 plus 2 sine of x Now we're ready to just straight up integrate. So the integral of cosine is going to be sine over like a inside of the value, and then the integral of sine is negative cosine. So x over 2 minus sine of 4x over 8 minus x over 2 plus sine of 2x over 4 minus 2 cosine of 2x over 2 plus cosine of x plus c. That should be the final integrand, which means that now we actually we can just plug this in and find the real volume. If I took the derivative of this, I would get back to this. I would get back to this step. I wouldn't actually get back to the final thing here. That's a note. When you use trig substitution, or you use things like theta equals sine of x, it doesn't actually go back to how it's going to be originally. It'll go back to whatever sub you used originally. So if you do want to take the derivative as a double check and it doesn't come out to what it was before, you could have done it right. You just may have switched it into a form that isn't quite the same. I'm not going to plug in these numbers because it doesn't make sense. I will do it off screen.